Empty space is boiling. Right now, in the room around you, quantum fields churn with hidden energy. Physics can calculate exactly how much. The answer is wrong. Wrong by a factor carrying 120 zeros, the worst prediction science ever made. We're going to walk straight into that error. Past plates shoved together by nothing at all, past a universe speeding up when it should be slowing down, toward a discovery in 2025 that shook the whole thing loose. If cosmic mysteries pull at you, a quick like or subscribe helps this channel grow. Prepare yourself, we begin. Picture the emptiest place you can imagine. Not the room around you, which is packed with air. Go further out, past the moon, past the planets, into the black gulf between the stars. Pull out every atom, pull out every speck of dust, pull out every stray particle of light until nothing remains. You now have a perfect vacuum. And here is the strange part. That perfect nothing is one of the busiest places in the entire universe. For a long time, people thought empty space was exactly what it looked like. A stage, a container, a silent backdrop where the real action happened. The stars did things, the planets did things. The space between them just sat there, doing nothing, waiting. That picture is dead wrong. When physicists learned to look at the vacuum through the lens of quantum theory, they saw something that made no sense at first. The emptiness was alive. It flickered. It trembled. Deep down at the smallest scales, space itself was seething with a restless energy that never switched off and never calmed down. Think of the ocean seen from an airplane. From high up, the surface looks flat and glassy, a smooth blue sheet. Then you drop down close, right to the waterline, and you see it was never smooth at all. It is a churning field of ripples and foam, moving every second. The vacuum is like that. From far away it looks like perfect stillness. Up close, at the scale of the tiniest things that exist, it froths. This froth has a name. Physicists call it the quantum vacuum, and it carries energy, real energy, woven into the fabric of empty space, present in every cubic inch of the cosmos, from the core of the sun to the loneliest void between galaxies. For most of history, this was unthinkable. The greatest thinkers of the ancient world argued that a true nothing could not even exist. That empty space was a contradiction. Later scientists imagined space as a passive emptiness, a stage swept perfectly clean. The idea that emptiness could hold energy, could tremble, could push on things, would have sounded like madness. Then the 20th century arrived and a new physics of the very small crept in and rewrote the meaning of nothing. It revealed that the deeper you look into the void, the more crowded it becomes. What seemed like the ultimate silence turned out to be a roar, just pitched too low and too small for us to hear, and that roar carries a weight that gravity itself must answer to. That single idea would go on to trigger the biggest embarrassment in the history of science. Because once you accept that empty space holds energy, the very next question is obvious. How much? And when the sharpest minds in physics sat down to add it up, using rules that had passed every test ever thrown at them, they got an answer so absurd it should have destroyed the universe before it began. We will get to that number. It is worse than you are imagining. But first we have to understand why the vacuum refuses to be still in the first place. Why can you not simply drain all the energy out of empty space and leave it truly, perfectly quiet? The answer lives inside a rule so deep that it forbids stillness itself. A rule that says nothing in this universe is ever allowed to be completely at rest. That rule is where the trouble starts. Try to hold something perfectly still, really still, not shaking even a little, not moving at all, frozen in one exact spot forever. In the everyday world you can get close. In the quantum world it is flatly impossible, and that impossibility is the seed of everything that follows. The reason comes from one of the strangest laws in all of science, a law that governs the smallest pieces of reality. It says that you can never know two things about a tiny particle at the same time with perfect sharpness. The more precisely you pin down where something is, the more fuzzy its motion becomes. Pin down its motion and its position smears out. You are allowed to know one clearly. Never both. This limit is woven into reality itself, deeper than any flaw in our instruments. The universe simply refuses to let anything be fully nailed down. Now watch what that does to stillness. To hold a particle perfectly still, you would need to know exactly where it is and know that it has exactly zero motion, both at once, perfectly. The universe forbids that combination, so a particle can never sit at a dead stop. Even at the coldest temperature possible, colder than the deepest reaches of space, it keeps jiggling. It has a tremble it can never lose. Physicists call that leftover tremble zero-point energy. It is the energy of motion that stays behind after you have removed every other scrap of energy you possibly can. It is the floor beneath the floor, the minimum, the jitter that never dies. Imagine trying to balance a marble at the very bottom of a bowl. In the ordinary world, it settles and stops. In the quantum world, the marble can never fully settle. It always keeps a faint shiver, forever rolling a hair's breadth back and forth, because being perfectly parked at the bottom would mean knowing its position and stillness together, and that is banned. Now here is the leap that changes everything. Empty space is filled with fields. A field is like an invisible substance spread through all of space, and it can ripple. The electric and magnetic fields are examples. So is the field tied to every kind of particle in nature. And each of these fields behaves like a countless collection of tiny springs, each one able to bounce. Springs that can bounce are exactly the kind of thing the rule acts on, so not one of them is ever allowed to be perfectly still either. Every field, everywhere, keeps its own quantum tremble, which means empty space is not empty of energy. It carries the combined jitter of every field there is. That is where the vacuum gets its restless energy. It is the sum of countless tiny shivers that the laws of the universe will not let go quiet. So far, so strange, but not yet a disaster. A tiny tremble in empty space sounds harmless enough. The disaster comes when you start counting how many trembles there are, and how strong each one can be. Before we count, though, there is something even weirder happening in that froth. The vacuum does more than shiver, it manufactures things. Whole particles appearing out of nothing and vanishing again, faster than the universe can notice they were ever there. Something appears out of pure nothing. It exists for the briefest flicker, then it disappears and the books are balanced as if it never happened. This is real. It happens everywhere in empty space, constantly, right now, all around you. To see how this is possible, we need one more piece of that same deep rule from before. The rule does not only blur position and motion, it also blurs energy and time. Over a very short stretch of time, the amount of energy in a patch of space becomes fuzzy, uncertain, undefined, and nature is happy to exploit that fuzziness. Here is the loophole. For an incredibly brief moment, a tiny patch of vacuum can hold more energy than it should, as long as it pays the debt back fast enough. The shorter the moment, the bigger the loan it is allowed to take, and with borrowed energy, you can make particles, because energy and matter are two faces of the same coin. So the vacuum does exactly that. It borrows energy from nowhere, and uses it to conjure pairs of particles into being. A particle and its mirror image partner blink into existence together, hang there for the tiniest instant, then slam back together and annihilate, returning the borrowed energy before the universe can catch them cheating. Physicists call these fleeting things virtual particles. They are the froth made visible. Everywhere in space, all the time, these pairs are boiling up and vanishing, an endless churn of ghostly matter that never quite finishes forming before it is gone. Think of a pot of water heated just below boiling. Tiny bubbles form at the bottom, rise a fraction, then collapse before they reach the surface. They appear, they vanish, over and over, faster than you can track any single one. The vacuum is that pot. The bubbles are pairs of particles forever surfacing and forever popping, an endless simmer running through every corner of space. The strangest part is that this simmer never stops and never runs out. The vacuum is not spending some stored supply of particles that will one day be gone. It conjures them fresh in every instant, everywhere at once, and has done so since the universe began. The emptiness is a bottomless engine of creation and destruction. Now, you might think something this ghostly could never touch the solid world. A particle that exists for less than a blink, that pays back its debt before anyone can measure it, surely leaves no mark. That would be a reasonable guess. It would also be wrong. These borrowed particles push, they pull, They nudge real matter in ways we can measure with staggering precision. The froth of the vacuum reaches out and lays its fingers on the ordinary world, and it leaves fingerprints. For decades, this was theory. Beautiful mathematics that predicted a boiling emptiness, with no way to prove the pot was really bubbling. Skeptics could shrug and say the whole thing was a fantasy of the equations, a story with no evidence behind it. Then, in the years right after the Second World War, an experiment caught the vacuum in the act. Someone measured a single atom carefully enough to see it being kicked around by particles that were not supposed to be there. The empty space around that atom was proven beyond any doubt to be full of invisible activity. That measurement was the first crack in the door. And what came pouring through it would eventually break physics wide open. In 1947, a quiet experiment on a single kind of atom produced a result that should have been impossible. And that impossible result was the first solid proof that empty space is full. The atom in question was hydrogen, the simplest atom in the universe. One heavy center, one tiny electron circling it. Nothing could be more basic. Physicists thought they understood it completely. They had equations that predicted with beautiful precision exactly how much energy the electron should have as it sat in its various orbits. Those predictions were clean, sharp, and supposedly final. A scientist named Willis Lamb decided to test them. Not because he expected a surprise, but because good physics means checking even the things you're sure of. He built an experiment delicate enough to measure the energy of that electron more precisely than anyone before him. The measurement did not match the prediction. The gap was tiny, almost laughably small. Two orbits that the equation said should have exactly the same energy turned out to have slightly different energies. Something was nudging the electron, shifting its energy by a hair, in a way the clean equations had never accounted for. There was nothing there to do the nudging. No other particle, no stray force. The electron was circling in what should have been empty space, and yet something was pushing on it. That something was the vacuum. The froth of virtual particles, the boiling pot of empty space, was reaching out and jostling the electron as it orbited. Countless ghostly particles popping in and out of existence around the atom were giving the electron a constant, gentle buffeting. Each individual kick was nothing. Added up, they shifted its energy by exactly the tiny amount Lamb had measured. Picture a small boat sitting on what looks like a calm harbour. Watch closely and you notice the boat trembling, rocking ever so slightly, even though the water seems flat. The trembling tells you the water is not truly still. It is full of tiny ripples too small to see directly, betraying themselves only through the movement of the boat. The electron was that boat. The vacuum was that restless water. This result, later called the Lamb shift, was a bombshell. It meant the boiling vacuum was real. The virtual particles were real. The froth that the equations had predicted actually existed, and it left a measurable print on the most ordinary atom in the cosmos. Empty space had been caught doing something. Willis Lamb won the Nobel Prize for that measurement, and physics was forced to accept a new picture of reality. The vacuum was a participant. It shaped the behavior of atoms. It could not be ignored. But proving the froth was real only sharpened the danger lurking underneath. Because if the vacuum truly holds all this activity, all these particles, all this restless energy, then it must add up to some total amount of energy per patch of space. A real number, a measurable quantity. And nobody had yet dared to calculate what that total would be. Before we face that number, there is an even more dramatic proof waiting. An experiment where the emptiness between two objects reaches out and shoves them together with a force you can actually feel. The vacuum does not only kick atoms, it can push solid metal. Take two flat metal plates, bring them very close together in a perfect vacuum, with nothing between them at all. According to the old picture of empty space, nothing should happen. According to reality, the plates get pushed together by a force coming from the nothing itself. This should sound insane. It is also true, and it was measured. The prediction came from a physicist named Hendrik Casimir in 1948, 1 year after the atom got kicked. He was thinking hard about the froth of the vacuum, and he realized something clever about what happens when you put two plates close together. Remember that empty space is filled with fields, and those fields are always rippling with their tiny quantum trembles. Those ripples come in every possible size. Long, slow waves and short, fast waves, all mixed together, filling all of space. Now slide two metal plates very close facing each other. In the narrow gap between them, only certain ripples fit. A wave has to fit neatly between the plates, the way only certain notes fit on a guitar string of a fixed length. The big, long ripples get shut out of the gap. They simply do not fit. But outside the plates, in the open space around them, every ripple is still allowed. So now there are more ripples pushing on the plates from the outside than from the inside. The froth outside is denser than the froth in the gap. And that imbalance creates a real, physical push. The outside vacuum shoves harder than the inside vacuum, and the two plates get pressed together. Think of two ships floating side by side on a choppy sea. Waves hit them from all directions, but in the narrow channel between the hulls, the biggest waves cannot form. So the water outside pounds the ships harder than the water between them, and the two hulls get nudged toward each other. Sailors have known this effect for centuries. Casimir realized the vacuum does the very same thing, using ripples of empty space instead of water. For decades, this stayed a prediction on paper. The force is fantastically weak, far too small to notice in daily life. Measuring it meant lining up two surfaces almost perfectly, a hair's breadth apart, and detecting a push fainter than the weight of a speck of dust. Then, in 1997, a physicist named Steve Lamoureux pulled it off. He measured the force between two surfaces held incredibly close in a vacuum, and there it was, a push, coming from the emptiness, matching Casimir's prediction almost exactly. The vacuum had reached out and moved solid objects. This was proof of a whole new order. The energy of empty space was no longer just a subtle nudge on an electron. It was a force strong enough to press metal together, measured in a lab, confirmed by the numbers. The froth was undeniably real, undeniably energetic, undeniably there. Which brings us back to the question that will not go away. If empty space holds this much energy, this much push, this much restless activity, then how much energy is in there, total? What is the actual amount per cubic inch of nothing? To answer that, physicists had to add up every ripple, every field, every tremble across all of space. And when they finally did the sum, the mathematics did something no one was ready for. It handed back infinity. The equations gave an answer of infinity. Not a big number, not an enormous number. Infinity, the answer that means the calculation has broken. And instead of admitting defeat, physicists invented a way to make the infinity disappear. Some of them called it a swindle. It also happened to work perfectly. Here is how the trouble arose. When you use quantum theory to calculate almost anything real, the force between two particles, the energy of an atom, the froth of the vacuum, the math involves adding up contributions from those endless virtual particles. And when you add up all of them, including the ones with more and more energy packed into smaller and smaller spaces, the sum grows without limit. It runs off to infinity. That is a catastrophe. A theory that predicts infinity for a real measurement is a theory that predicts nonsense. You cannot weigh infinity. You cannot measure infinity in a lab. Every experiment gives a finite, sensible number. So the theory and the world were in flat contradiction. For years, this nearly killed quantum physics. The equations were clearly onto something, matching experiments in the parts that worked, yet vomiting infinity whenever you pushed them too hard. Some of the greatest physicists of the age were stuck. The escape came in the years after the war, from a handful of brilliant minds working in parallel, including Richard Feynman. They found a procedure, a piece of mathematical surgery that could cut the infinities out. The trick was to notice that the quantities blowing up, like the raw mass and charge of a particle, were never things you measured directly anyway. What you actually measure is the particle wrapped in its cloud of vacuum froth, all bundled together, so they performed a swap. They took the infinite pieces and folded them into the definitions of mass and charge, then set those equal to the real, measured, finite values from experiments. The infinities on one side got quietly absorbed into the numbers on the other, and what remained, once the dust settled, were finite predictions that matched reality to breathtaking accuracy. This procedure is called renormalization, and it is one of the most successful tools ever invented. It lets physicists predict certain quantities correctly to more than 10 decimal places, an agreement between theory and experiment so tight it is like measuring the distance across a continent and being off by less than the width of a hair. But not everyone loved it. Paul Dirac, one of the founders of the whole field, hated it to the end of his life. He called it a way of sweeping infinity under the rug. To him, a theory that produced nonsense and then hid the nonsense by hand was a theory that was secretly broken, no matter how well the leftover numbers came out. Dirac's discomfort matters because renormalization is a tool for differences and ratios. It shines when you are comparing one measurement to another, and the infinities cancel between them. It works when you never have to state the raw, absolute energy of the vacuum on its own. There is one thing, though, that cares desperately about the absolute energy of empty space. Not the difference, not the ratio, the total, standalone amount. And that thing is gravity. The moment you ask gravity what it thinks of the vacuum's total energy, the swindle stops working and the real monster wakes up. Add up the energy of every ripple in empty space, all the way down to the smallest scale nature allows, and you get a number. That number is so large that if it were true, the universe would have ripped itself apart in its first instant, and the mathematics insists it is true. Let us actually do the sum the way a physicist would. Empty space is full of fields, and each field is trembling with its 0-point jitter, that unavoidable minimum energy from before. Each little tremble carries a small amount of energy. To find the total, you add them all up. The problem is how many there are. The trembles come in every size, from long lazy ripples down to tighter and tighter ones. And here is the crushing part. There is no natural stopping point as you head toward the small end. You can always cram in a ripple half the size of the last one, holding a little more energy, and then one half that size again and again, packing in more and more energetic trembles as the scale shrinks. Physicists do impose a floor, the smallest length where our current physics still makes any sense, a fantastically tiny distance called the Planck scale. Below it, we simply do not know the rules. So they add up every tremble down to that floor and stop. The total is monstrous. The energy packed into every cubic inch of empty space, according to this calculation, is so vast that a single teaspoon of vacuum would contain enough energy to dwarf everything we see. And energy, through the rules of gravity, bends space and pulls on the cosmos. An energy density that huge would have gravitational effects beyond imagining. If the vacuum truly held that much energy, its gravity would have curled the universe up into a tiny knot the instant it was born, or blasted it apart faster than any structure could form. Galaxies could never assemble. Stars could never light. Atoms could never gather. The cosmos would have been strangled in its cradle, in less time than it takes light to cross the width of a single atom. Picture trying to build a house of cards inside a raging hurricane. The winds are so violent that no card can rest on another for even a heartbeat. That is what the predicted vacuum energy would do to the universe. Nothing could hold together. Nothing could last. Reality itself would be torn to shreds. And yet, look around. The universe is calm. It is vast and old and full of structure. Galaxies wheel slowly through billions of years. Stars burn steadily. You exist, made of atoms that have held together for a very long time. The house of cards is standing, tall and quiet, exactly as if there were no hurricane at all. So the vacuum energy that the mathematics screams should be there is somehow almost entirely missing from the actual behavior of the cosmos. The theory and the universe are staring at each other across an impossible gulf. This is the mistake. The one physicists cannot explain, cannot ignore, and cannot make go away. But before we measure just how enormous the gulf really is, we need to meet the strange character on the other side of it. A number that a certain famous physicist added to his equations, then called the greatest blunder of his career. In 1917, the most famous physicist alive did something he would come to regret. He looked at his own equations, saw an answer he did not like, and quietly inserted an extra number to make the universe behave. That number would haunt physics for the next 100 years. The physicist was Albert Einstein, and the equations were his masterpiece, the theory of gravity we call general relativity. It described gravity in a completely new way, as the bending of space and time by matter and energy. It was gorgeous. It was powerful. And when Einstein used it to describe the whole universe, it told him something he refused to accept. The equation said the universe could not sit still. According to his own theory, a cosmos full of matter should be moving. All that matter pulls on all the other matter through gravity, so the whole universe should be collapsing inward, falling together under its own weight, on its way to crushing itself into a point. Einstein did not believe that. In his time, everyone assumed the universe was static, eternal and unchanging. The stars were fixed. The cosmos had always looked the same and always would. A collapsing universe was unthinkable, so Einstein cheated, elegantly. He added a new term to his equations by hand, a constant number that acted like a gentle outward push spread evenly through all of space. He tuned this push to exactly balance the inward pull of gravity. With the two forces cancelling, the universe could hang motionless, poised and eternal, just as everyone believed it should be. He called this new term the cosmological constant. In the equations, it was represented by a single Greek letter, lambda. Its whole job was to hold the universe still. Think of a heavy weight hanging from the ceiling by a spring. Gravity pulls the weight down, the spring pulls it up. Tune the spring just right and the weight hangs perfectly still, balance between the two. Einstein's constant was that spring tuned to hold the entire cosmos in a frozen balance against the crush of its own gravity. There was something uncomfortable about it, and Einstein knew it. The balance was fragile. Nudge the universe a little too far one way and it would collapse. Nudge it the other way and it would fly apart. A perfectly balanced universe is like a pencil standing on its tip. It works only if nothing ever disturbs it, and something always does. Still, the fix did its job on paper. The universe stood frozen. And for over a decade, Einstein carried this extra number in his equations, a made-up push with no known cause, invented purely to force the cosmos to match what everyone expected. He had no idea he had accidentally written down one of the deepest quantities in nature. He thought lambda was a bookkeeping trick, a fudge factor he could delete the moment it proved unnecessary. That moment was coming. Out in California, an astronomer was about to point the largest telescope in the world at the distant galaxies and discover that the universe was doing the one thing Einstein had built his constant to forbid. It was moving, and when Einstein learned the truth, he would tear his beloved constant out of the equations and curse the day he ever wrote it down. An astronomer in California pointed a giant telescope at the sky and caught the entire universe in the act of flying apart. The discovery shattered the idea of a static cosmos overnight, and it drove Albert Einstein to delete his cosmological constant and call it the biggest mistake of his life. The astronomer was Edwin Hubble, working at the Mount Wilson Observatory with the most powerful telescope on Earth. In the 1920s, he was measuring the light from distant galaxies, faraway islands of stars scattered across the dark. And he noticed something bizarre about that light. The light from nearly every galaxy was stretched. Its colour was shifted toward the red end of the rainbow, as if the waves of a light had been pulled longer on their journey to us. This stretching happens when a source is moving away from you. The faster it flees, the more the light stretches. Almost every galaxy was fleeing, and the farther away a galaxy was, the faster it was running from us. That was the key. The pattern meant one clear thing. The galaxies were not scattering at random. The universe itself was expanding. Every galaxy was rushing away from every other galaxy, like dots painted on a balloon that someone is blowing up, each dot drifting away from all the others as the rubber stretches. The static universe was dead. The cosmos was not frozen and eternal. It was growing, expanding, changing, exactly as Einstein's raw equations had predicted before he tampered with them. This landed hard. If Einstein had trusted his own theory in 1917, if he had left it alone, the mathematics would have told him the universe must be expanding years before anyone looked. He could have predicted the greatest discovery in the history of astronomy. Instead, he had smothered that prediction under a made-up constant, all to protect a belief that turned out to be false. Einstein was furious with himself. He threw the cosmological constant out of his equations, sending lambda to zero, erasing it completely. With the universe expanding on its own, there was no need for a balancing push. The fudge factor had been pointless all along. According to the story that spread through physics, Einstein called the cosmological constant the biggest blunder of his life, Picture an inventor who builds an elaborate machine to solve a problem, only to learn the problem never existed. Embarrassed, he smashes the machine and vows never to speak of it again. That was Einstein and his constant. He had built a beautiful, unnecessary contraption, and he wanted it gone. For most of the 20th century, that was the verdict. The cosmological constant was a mistake, a relic, a cautionary tale told to physics students about the danger of forcing nature to fit your assumptions. Lambda was zero. Case closed. The constant, though, was not finished. It had a secret that neither Einstein nor Hubble had noticed. That extra number, that push spread evenly through all of space, behaved exactly like one thing in nature. It behaved like the energy of the vacuum itself, and that meant Einstein had not invented a meaningless fudge factor at all. He had accidentally written down the very quantity that quantum physics would later calculate to be catastrophically, impossibly huge. The blunder was about to come back from the dead. The number Einstein deleted refused to stay dead. Physicists discovered that his discarded constant and the boiling energy of the quantum vacuum were secretly the same thing. Two ideas born in completely different worlds turned out to describe one identical push on the cosmos. To see why, look closely at what Einstein's cosmological constant actually did in his equations. It represented an energy spread perfectly evenly through all of space. Every point in the universe carried the same amount of it. It did not clump. It did not thin out as the universe grew. It was a smooth, unchanging energy filling the entire void, and it pushed space to expand. Now recall what the quantum vacuum is. It is an energy spread perfectly evenly through all of space. Every point carries the same restless froth. It does not clump. It does not thin out. It is a smooth background energy filling the entire void. Those two descriptions are word for word the same. This was the shocking realization. The energy of empty space, calculated from quantum theory, behaves in Einstein's equations exactly like his cosmological constant. They are not two separate things that happen to look alike. They are one thing seen from two directions. The froth of virtual particles and the lambda that Einstein cursed are the same entry in the great equation of gravity. That connection is a bridge between the two mightiest theories in physics, and it is a trap. On one side stands quantum theory, the physics of the tiniest things, which insist the vacuum holds a specific energy. On the other side stands general relativity, the physics of gravity and the cosmos, which takes any energy in empty space and turns it into a push on the universe. The bridge between them is the vacuum energy, which is the cosmological constant, which is lambda. So the two theories are forced to talk to each other through this single number. Quantum theory calculates how much energy is in the vacuum. General relativity takes that number and tells you what it does to the expansion of space. Whatever the quantum froth adds up to, gravity will feel it, and the whole universe will respond. Imagine two engineers who have never met, working on opposite sides of a mountain, each drilling a tunnel. If their measurements agree, the two tunnels should meet perfectly in the middle. Quantum theory drilled from one side, calculating the vacuum energy. General relativity waited on the other side, ready to receive that number and turn it into the behavior of the cosmos. The two tunnels were about to meet. They missed each other by the largest margin in the history of science, because quantum theory's answer for the vacuum energy, that monstrous sum from before, was gigantic, and general relativity said that if the vacuum truly held that much energy, the cosmos would be violently, catastrophically distorted. Yet the real universe showed almost none of it. The number coming out of the tiny world and the number the cosmos actually obeyed were wildly, absurdly different. For a while, physicists clung to a hope. Maybe, by some deep principle nobody had found yet, the true vacuum energy was exactly zero. Maybe everything cancelled perfectly. Lambda really was gone, and the mismatch would vanish. It was an uncomfortable hope, but it was survivable. Then, in 1998, two teams of astronomers measured the expansion of the universe and found that lambda is not zero after all. In 1998, two rival teams of astronomers, racing each other across the sky, made the same shocking discovery at almost the same moment. The universe was doing something no one had predicted. It was speeding up, and nothing they knew could explain what was pushing on it. Both teams were chasing the same goal. They wanted to measure how fast the expansion of the universe was slowing down. Everyone expected it to be slowing. After all, the cosmos is full of matter, and matter pulls on matter through gravity. All that gravity should be acting like a brake on the expansion, gradually reining in the flying galaxies, slowing the whole grand outrush. To measure the slowdown, they needed a way to gauge distances across billions of years of cosmic history. They found it in a special kind of exploding star. Certain stars die in a blast that always shines with very nearly the same true brightness anywhere in the universe. Physicists call them a standard kind of beacon. If you know how bright the explosion truly is, and you see how dim it looks from Earth, you can work out exactly how far away it happened. And by catching the stretch in its light, you can tell how much the universe has expanded since that light set out. So the two teams hunted these dying stars in distant galaxies, gathering their faint light, measuring their distances and their stretch. One team was the Supernova Cosmology Project. The other was the High Z Supernova Search Team. They were competitors, working separately, each hoping to be first to measure how the cosmic break was slowing the universe down. The data came in, and it made no sense. The most distant explosions were fainter than they should have been, too faint, which meant they were farther away than a slowing universe could explain. The only way to make the numbers work was almost too strange to say out loud. The expansion of the universe had not been slowing down at all. At some point in the past, it had switched to speeding up. The galaxies were flying apart faster and faster with every passing eon. Both teams found it, independently, at the same time. Neither wanted to believe it, because there was no known force that could do this. Gravity pulls things together. It slows expansion. It does not push the whole universe to accelerate. Something else, something nobody could see, was flooring the cosmic accelerator. Imagine throwing a ball into the air and expecting it to slow, stop, and fall back down. Instead, the ball speeds up as it climbs, racing away from your hand faster and faster, hurled upward by an invisible hand you cannot detect. That is what the universe was doing. Every galaxy was that ball, accelerating outward, pushed by a force with no name. The discovery was so momentous that the leaders of both teams later shared the Nobel Prize. The universe was accelerating. It was a fact now, carved into the data, confirmed twice over by rivals who checked each other's work. Whatever was doing the pushing got a name. Physicists called it dark energy, a placeholder for a mysterious something spread through all of space, driving the cosmos apart. And when they looked at how it behaved, at the way it pushed evenly and relentlessly through the void, they felt a chill of recognition. Dark energy looked exactly like Einstein's resurrected constant. It looked exactly like the energy of the vacuum. Dark energy does something gravity is not supposed to do. It pushes outward. Everything else in the universe, every star and planet and galaxy, uses gravity to pull things together. Dark energy uses it to drive things apart, and that single reversal is the key to everything. To understand how this is possible, you have to give up a comfortable idea. We usually think gravity responds only to mass, more pull. But Einstein's theory says gravity responds to energy, and to something subtler as well. It responds to pressure, and pressure can work in surprising directions. Ordinary things have ordinary pressure. The air in a balloon pushes outward on the rubber. That is positive pressure. But some things can have the opposite, a kind of inward tension, like a stretched rubber band pulling its ends together. Physicists call that negative pressure. And here is the twist that changes the fate of the universe. In Einstein's equations, strong negative pressure creates a gravitational push, not a pull. Dark energy has exactly this strange property. It fills space with energy, and along with that energy comes a powerful negative pressure, a tension woven into the vacuum. That tension, through the rules of gravity, drives space itself to expand. The more space there is, the more dark energy there is to push it, so the expansion feeds on itself and accelerates. This is where dark energy and the vacuum froth lock together perfectly. The energy of empty space, that boiling quantum froth, carries precisely this kind of negative pressure. If the vacuum has energy, it automatically pushes the universe to expand. The quantum froth is a live candidate for the very thing accelerating the cosmos. Think of the vacuum as a sea of tightly coiled springs filling all of space, each one straining. That coiled tension is the negative pressure. Let it act on the fabric of space, and instead of pulling inward, it flings the whole universe outward, harder and harder, forever. So now the pieces snap into place with terrible clarity. Einstein invented a constant to push against gravity. He deleted it in shame. Quantum physics revealed that the vacuum holds energy, and that this energy behaves precisely like that same constant. Then astronomers caught the universe accelerating, driven by a mysterious push spread evenly through space. 3 separate threads, and all of them point to the same object. The energy of empty space is real, it is non-zero, and it is shoving the cosmos apart right now. That should have been a triumph. Quantum theory predicted the vacuum has energy. The universe is accelerating as if the vacuum has energy. The prediction and the observation seem to agree. For one shining moment, it looks like physics nailed it. Then somebody compared the two numbers. On one side, the amount of vacuum energy that quantum theory calculates. On the other, the amount of dark energy the universe actually contains, measured from the acceleration. These two numbers describe the same thing. They should match. If the vacuum froth is the dark energy, then the calculated value and the observed value must be equal, or at least close. They are not close. They are so far apart that the gap between them is almost impossible to write down, and when physicists finally lined the two numbers up side by side, they were staring at the single worst prediction any scientific theory has ever made. Two numbers sit side by side. One comes from the deepest theory of the tiny world. The other comes from watching the actual universe expand. They are supposed to be the same number. When you finally place them next to each other, the disagreement is so violent it feels like a joke. Let us be very clear about what these two numbers are, because the whole crisis lives in the gap between them. The first number is the theoretical one. Quantum theory says empty space is full of froth, full of zero-point trembles from every field, and when you add them all up down to the smallest scale we trust, you get a specific energy for each patch of vacuum. That is the calculated vacuum energy. It is enormous, the monster from before, the value that should have strangled the universe at birth. The second number is the measured one. Astronomers watched the universe accelerate. From the rate of that acceleration, they worked out how much dark energy actually fills space. Since dark energy behaves exactly like vacuum energy, this measured amount is the real observed energy of empty space, read straight off the behavior of the cosmos. Both numbers describe the energy in a patch of vacuum. The theory predicts one value. The universe reveals another. In a healthy science, the prediction and the measurement line up. Maybe with a small gap you can chase down and explain. Here the gap is not small. The measured energy of empty space is fantastically, unbelievably tiny compared to the calculated one. Real space holds only the faintest whisper of vacuum energy, just enough to gently accelerate the cosmos over billions of years. The theory demanded a screaming torrent. The universe delivered a whisper, and the ratio between the torrent and the whisper is a number with so many zeros that it strains the mind to hold it. Imagine two people are asked to guess how much a grain of sand weighs. The first person, using careful reasoning, confidently announces that the grain weighs more than every star, planet, and galaxy in the observable universe combined. The second person walks over, puts the grain on a scale, and reads off a weight lighter than a speck of dust. That is the scale of the disagreement between what quantum theory predicts for the vacuum and what the universe actually contains. This is a failure unlike any other in physics. Usually when a theory is wrong, it is a little wrong. It gets the answer off by a few percent, or by a factor of 2, or maybe 10. You can imagine fixing that with a small correction. But here the theory is not off by a factor of 10, or 1,000, or 1,000,000. It is off by so much that no ordinary mistake could ever produce it. And the source of this failure is the most successful theory ever built. Quantum theory, the very framework that gives this insane answer, has passed every test we know how to run. It predicts other quantities correctly to more decimal places than any theory in history. It has passed every test. It is right about almost everything, except this. On the one question of how much energy fills empty space, the most accurate theory humanity has ever created produces the most spectacularly wrong answer humanity has ever recorded. Exactly how wrong? It is time to say the number out loud and to feel the full weight of it. Physicists have a name for the gap between what quantum theory predicts for the vacuum and what the universe actually contains. They call it the worst theoretical prediction in the history of physics. And when you learn the size of the error, you understand why they are not exaggerating. The mismatch is measured in orders of magnitude. An order of magnitude means a factor of 10. Off by 1 order of magnitude means off by 10 times. Off by 2 orders of magnitude means off by 100 times. Off by 3 means 1,000 times. Each step adds another 0, another tenfold jump in the size of the mistake. Being off by 3 or 4 orders of magnitude is already a serious failure for any theory. It means your prediction and reality differ by thousands. That would be a scandal in most branches of science. The vacuum energy prediction is not off by 3 orders of magnitude. It is off by around 120. Sit with that. 120 orders of magnitude. That means the calculated value and the measured value differ by a factor of 10 multiplied by itself 120 times. A 1 followed by 120 zeros. A number so vast it has no name and no use anywhere else in science. There is nothing to compare it to because nothing else in physics is ever wrong by that much. To put that error in perspective, consider a comparison physicists themselves use. Suppose an engineer sets out to measure the length of a bridge and makes an error of 120 orders of magnitude. Their answer would be off by a distance far larger than the width of the entire observable universe. The error alone would not fit inside all of space. That is the failure hiding at the heart of our best theory of nature. It is why physicists reach for words like catastrophe and embarrassment when they talk about it. Some call it the largest disagreement between theory and experiment in all of science. Others simply call it the worst prediction ever made. Sit with how strange this situation truly is. Quantum field theory, the source of the giant number, is the crown jewel of modern physics. It underlies our understanding of every force except gravity. It has been confirmed in thousands of experiments. When it comes to almost every question you can ask it, it gives answers of unearthly precision. Then you ask it the simplest question of all. How much energy is in empty space? And this flawless, battle-tested theory hands you a number wrong by more zeros than there are atoms in your body. A comparison this severe cannot be a small oversight. You cannot patch a 120 order of magnitude hole with a minor correction. A gap this size is screaming that something deep, something fundamental, is broken or missing in our picture of reality. But there is a way to make this monstrous number even more real, even more visceral. Because a 1 with 120 zeros is just a symbol on a page, until you try to actually picture it. And when you do, the disaster stops being an abstract number and becomes something you can almost feel in your gut. A number with 120 zeros is easy to write and impossible to feel. Your mind slides right off it. So let us build the number up, step by step, until the sheer madness of it lands, and you finally sense how badly the theory failed. Start small. The number 1000 has 3 zeros. You can picture 1,000 people in a stadium section. Easy. 1,000,000 has 6 zeros. That is a large crowd, a small city. Still imaginable? Barely. 1,000,000,000 has 9 zeros. Now you're past what anyone can truly picture. 1,000,000,000 seconds is more than 30 years of your life. Every single second counted. Keep climbing. The number of grains of sand on every beach and in every desert on the whole planet is often estimated at a number with around 20 zeros. Every grain on every shore, in every dune, everywhere on Earth. 20 zeros. The number of stars in the entire observable universe, every star in every galaxy across all of visible space, is a number with around 23 zeros. Every sun you could ever see in every galaxy that exists adds up to just 23 zeros. Go further to the smallest count that still means anything. The number of atoms making up the entire planet Earth, every atom in every rock and ocean and mountain and living thing, is a number with roughly 50 zeros. The whole world, atom by atom, gives 50 zeros. Now push all the way to the top. Some physicists estimate that the number of atoms in the entire observable universe, every atom in every star in every galaxy across all of visible space, is a number with around 80 zeros. That is the count of everything. Every particle of ordinary matter in all the cosmos we can see, 80 zeros, and the error in the vacuum energy prediction is not 80 zeros, it is around 120. The mistake in our best theory is larger than the number of atoms in the entire observable universe, and then larger still by a factor with 40 more zeros stacked on top. There is no pile of real things anywhere, not sand, not stars, not atoms, not the whole material universe that reaches as high as the size of this error. The theory overshot everything that exists several times over in a way no collection of real objects can match. Picture a scale, an ordinary weighing scale. On one side, you place a single feather, standing in for the tiny, whisper-quiet energy the vacuum actually has. On the other side, to balance it, the theory tells you to place a weight equal to the mass of everything in the universe, piled up not once, but with dozens of extra universes stacked on for good measure. That is the balance the theory demanded. That is what it predicted the feather should weigh. This is the true face of the mistake. It is a gap so wide that no object, no quantity, no pile of anything real can span it. And that raises a question far stranger than the number itself. Because if the theory were even close to right, if the vacuum held anything like that energy, you would not be here to be baffled by it. The universe itself would never have existed, which means the mistake is a paradox, an error the universe disproves simply by existing. The vacuum energy prediction has a bizarre feature that sets it apart from every other failed idea in science. It disproves itself. The very fact that anyone is alive to calculate the number proves the number cannot be right. The universe is walking, breathing evidence against its own theory. Think about what would happen if the calculated vacuum energy were actually correct. That torrent of energy in every patch of empty space would carry with it, through the rules of gravity, an overwhelming push on the fabric of the cosmos. Space would not gently expand over billions of years. It would explode outward with unimaginable violence, or curl up and crush itself in a span of time so short it barely counts as time at all. In that universe, nothing could ever form. Matter would be ripped apart before a single atom could hold together. Two particles could never stay near each other long enough to bond. Gas could never gather into clouds. Clouds could never collapse into stars. Stars could never forge the heavier elements. Planets could never assemble. And life, which needs all of those things and billions of years of quiet stability on top of them, could never even begin. A universe with the predicted vacuum energy is a universe that lasts an instant and then tears itself to nothing, empty of structure, empty of stars, empty of observers, empty of everything. Yet here is our universe, old, vast, patient, full of galaxies that have wheeled slowly for billions of years, full of stars that have burned steadily long enough to cook up the atoms in your bones, full of planets, oceans, and living things, and full, at least on one small world, of curious minds able to sit down and calculate what the vacuum energy ought to be. Those minds are the disproof. Every scientist who has ever written down the enormous predicted value has done so inside a stable, ancient, structured universe. A universe that could not exist if the value were real. The prediction says reality should have been destroyed. Reality answers by continuing to exist, calmly, for as long as it takes to notice the contradiction. Imagine a doctor who examines a patient, runs the numbers, and declares with total confidence that this person died decades ago and cannot possibly be alive. Then the patient, sitting right there, asks the doctor to please explain the diagnosis. The living patient is proof the calculation went wrong somewhere. The vacuum energy prediction is that impossible diagnosis, and the entire universe is the patient calmly asking for an explanation. This is what makes the problem so much deeper than an ordinary error. A normal wrong prediction just disagrees with a measurement. You go back, find the flaw, fix it, move on. But this prediction disagrees with existence itself. It rules out the very cosmos that produced the physicists who made it. The failure is total and self-defeating, so the value the vacuum actually has must be almost inconceivably small compared to the theory. Small enough to let the universe survive. Small enough to let structure form. Small enough to let you exist. Almost, but not quite. Zero. And that word, almost, hides a second mystery, one that many physicists find even more maddening than the first. The vacuum energy is strangely, stubbornly poised just above zero, and explaining why it sits at that one particular tiny value splits the whole crisis into two separate nightmares. Physicists could have made peace with a vacuum energy of exactly zero. A clean zero feels like it might hide some deep reason, some perfect cancellation waiting to be discovered. What they got instead was far more disturbing. The vacuum energy is tiny, but it is not zero. And that single fact turns one hard problem into two. For decades before the universe was caught accelerating, most physicists quietly assumed the vacuum energy must be exactly zero. It was the only comfortable option. If the true value was zero, then maybe some elegant principle, some hidden symmetry in the laws of nature, forced everything to cancel out perfectly. All those enormous contributions from all those fields would add up, with careful plus and minus signs, to a flawless, absolute nothing. Nature would be tidy. The monster would cancel itself. That hope was clean. A perfect zero can come from a perfect reason. Physicists have seen it before, where a deep symmetry guarantees that some quantity vanishes exactly. So they waited for the symmetry that zeroed out the vacuum energy. Then 1998 arrived, and the universe was caught accelerating. The vacuum energy was measured, and it came back a real, positive value. It was tiny, almost nothing. A faint whisper of energy in each patch of space, yet real, positive, and driving the whole cosmos apart. The clean zero was gone forever. Nature had chosen a specific, tiny, non-zero value, and now physics had to explain that exact number instead of a comfortable nothing. This split the crisis into two distinct problems, and both are brutal. The first problem is the old one, the one we've been building toward. Why is the vacuum energy so small? Why is it around 120 orders of magnitude below what the theory screams it should be? What tames the monster, dragging that torrent down to a whisper? The second problem is newer and to many even nastier. If some principle drags the vacuum energy almost all the way down, why does it stop just short of zero? A perfect cancellation to exactly zero could come from a symmetry. But a cancellation that kills off 120 zeros of energy and then, at the very last digit, leaves behind one tiny surviving crumb is far harder to explain. What kind of mechanism cancels almost everything with unbelievable precision and then deliberately spares a whisper? Imagine a sculptor carving a mountain down to nothing. If they carve it perfectly flat to the ground, you might believe they followed a rule, a clean stopping point at zero height. But suppose they carve away the entire mountain, billions of tons of rock, and stop when exactly one single grain of sand is left standing on the bare ground. That is far stranger. Why stop at 1 grain? Why not 0? Why not 2? The leftover grain demands its own explanation, separate from the carving. The vacuum energy is that one surviving grain. Nature ground the mountain down through 120 orders of magnitude and left a crumb. Explaining that crumb is a mystery all its own. So physicists face two monsters instead of one. Why so small and why not 0? For a while though, there was a beautiful idea that seemed capable of slaying at least the first one. An idea so elegant that a whole generation of physicists bet their careers on it. It promised to cancel the monster with a perfect partner for every particle in nature. There was a solution so elegant that physicists fell in love with it. It promised to erase the vacuum energy monster automatically, using a hidden symmetry so perfect that everything would cancel to nothing. Its name was supersymmetry, and for a while it looked like the answer to everything. To understand how it works, you need one crucial fact about the vacuum froth. Not every field contributes to the vacuum energy in the same direction. The particles of nature come in two great families. One family builds up the vacuum energy, adding positive contributions to the froth. The other family does the opposite, subtracting, pulling the vacuum energy down. One family pushes the total up, the other pulls it down. Now imagine those two families were perfectly matched. Suppose for every particle that adds a certain amount of energy to the vacuum, there existed a partner particle that subtracts exactly the same amount. Every push would meet an equal and opposite pull. The positive contributions and the negative contributions would line up in perfect pairs and cancel, one by one, all the way down. The monstrous vacuum energy would erase itself completely, dropping to a clean, elegant zero. That is exactly what supersymmetry proposes. It says every known particle has a hidden partner, a kind of mirror twin from the opposite family. For every particle that pushes the vacuum energy up, there is a partner that pulls it down by the same amount. Pair them all up, and the enormous contributions cancel with mathematical perfection. The monster vanishes on its own. This was breathtaking. It meant the giant vacuum energy was never really a mistake in the theory at all. It was just a sum with half of its terms missing. Add in the partner particles, and the whole thing collapses to nothing cleanly, for a beautiful reason rooted in a deep symmetry of nature. Picture a perfectly balanced seesaw. On one side sit all the ordinary particles pushing down. On the other side sit their partners, pushing down with equal force on their end, which lifts the first side by the same amount. Every weight on one side is matched by an identical weight on the other, so the seesaw hangs perfectly level. That level balance is a vacuum energy of zero, achieved automatically by the pairing. Supersymmetry did more than tame the vacuum. It solved other deep puzzles in physics at the same time, and it offered a natural candidate for the mysterious dark matter that holds galaxies together. It was elegant, it was powerful, and it tied together loose threads all across physics. Whole careers were built on it. Thousands of papers were written. For decades it was the leading hope for the future of fundamental physics, the idea most likely to carry us into the next era of understanding. There was only one thing left to do: find the partner particles. If supersymmetry is true, then every ordinary particle has a hidden twin waiting to be discovered. Build a machine powerful enough, smash particles together hard enough, and those twins should appear, proving the whole beautiful picture in one stroke. So physicists built the most powerful machine in human history and went hunting for the partners. The fate of the most elegant idea in physics, and maybe the solution to the worst prediction in science, came down to what that machine would find buried in the wreckage of its collisions. It found nothing. The most powerful machine ever built went hunting for the partner particles that would have saved the most beautiful idea in physics. Year after year, it smashed matter together at almost the speed of the light, searching the debris. The partners never showed up, and their absence tore a hole in the theory that was supposed to cancel the monster. The machine is the Large Hadron Collider, a ring of tunnels buried beneath the border of France and Switzerland 17 miles around. Inside it, protons are whipped to nearly the speed of light and slammed head-on into each other, releasing bursts of raw energy in a tiny point of space. Out of that energy, new particles are born, flying outward into house-sized detectors that catch and measure every scrap of the wreckage. This is how you find new particles. Energy turns into matter in the collision, and the heavier the particle you want, the more energy you need. If supersymmetry is real, its partner particles should be heavy, but reachable. Build a collider powerful enough, and you should be able to conjure them straight out of the collision energy, then spot their tracks in the debris. The Large Hadron Collider was powerful enough. This was the machine that, in 2012, found the famous Higgs particle. It reached energies never touched before, and after finding the Higgs, it turned its full attention to the hunt everyone was waiting for, the search for the partners of supersymmetry. Physicists watched the debris of trillions of collisions. They knew exactly what the partner particles should look like, the kinds of tracks they would leave, the patterns of energy they would scatter into the detectors. They searched every corner of the wreckage, sifting mountains of data, looking for even a hint of a twin. They found the ordinary particles, over and over, exactly as the standard picture predicted. They found the Higgs. They confirmed the known world in exquisite detail. But the partners, the mirror twins that supersymmetry demanded, were simply not there. No new tracks, no unexplained energy, no sign of the hidden family that was supposed to cancel the vacuum monster. The machine kept running. It was upgraded to higher energies and set loose again, pushing the search further into heavier and heavier possible partners. Still nothing. The place where the partners were expected to appear came up empty. Then the next place, then the next. The collider swept through the natural hunting grounds of supersymmetry and returned with silence. Imagine setting 100 perfect traps in a forest where you are certain an animal lives. You have tracks, you have theory, you have every reason to expect it. You wait months, you check every trap. Everyone is empty because the animal, it seems, was never there. That was the collider and the partner particles. The traps were flawless. The quarry never came. This was a heavy blow. If the partner particles existed at the masses supersymmetry needed to work cleanly, the collider should have found them. Their absence did not quite prove the idea dead, because the partners could always be hiding at even higher masses beyond the machine's reach. But every empty search pushed them further out, into a range where the beautiful cancellation starts to fall apart. Because here is the cruel catch. Supersymmetry only cancels the vacuum monster perfectly if the partners are close in mass to the ordinary particles. The heavier and more distant the partners, the worse the cancellation becomes. And the collider had just pushed them very far away indeed. Supersymmetry only works its magic if the partners match their ordinary twins closely. The moment the partners turn out to be far heavier, the perfect cancellation cracks apart. And the collider's empty-handed search had just shoved those partners so far away that the beautiful solution stopped working. The monster came back, wounded but alive, returned to that perfectly balanced seesaw from before, with ordinary particles on one side and their partners on the other. When the two sides carry equal weights, the seesaw hangs level and the vacuum energy cancels to zero. That flawless balance is the whole point of supersymmetry. But that balance only holds if the partner particles have the same mass as their ordinary twins. If a particle and its partner weigh the same, their contributions to the vacuum energy match exactly, and they erase each other cleanly. The instant their masses differ, the cancellation fails. The seesaw tilts, and leftover energy survives. Here is the problem. If the partners had the same mass as ordinary particles, we would have found them long ago. A partner as light as an electron would have turned up long ago. Since we have never seen these twins, they must be much heavier than their ordinary counterparts. The symmetry, if it exists at all, must be broken, with the partners hauled up to far greater masses. And the LHC made this much worse. By searching and finding nothing, it proved that if the partners exist, they are heavier still, well beyond the lightest masses that would have made the cancellation nearly perfect. The bigger the gap between a particle and its distant, heavy twin, the more their vacuum contributions fail to match, and the more leftover energy is left uncancelled. So the seesaw no longer hangs level, it tilts, because the two sides carry very different weights. The vacuum energy no longer cancels to zero. A residue survives, set by how badly the masses fail to match. Now for the number that broke hearts. Even in the most generous version of this broken supersymmetry, with the partners placed as favourably as the experiments allow, the leftover vacuum energy is still gigantic. The cancellation trims the monster down, yes, it shaves off many, many orders of magnitude. But when you work out what remains, the broken supersymmetry still overpredicts the vacuum energy by something like 50 to 60 orders of magnitude. Let that comparison stand next to the earlier one. The raw theory was off by around 120 orders of magnitude. The best that broken supersymmetry can do brings that down to around 50 or 60. That is genuine progress. It is also a total failure. 50 orders of magnitude is still a disaster beyond anything else in science. You have cured half the disease and left the patient still impossibly sick. Picture a rescue crew draining a flooded valley. They pump out an ocean of water, dropping the level dramatically, and everyone cheers. Then they look again and realise the water is still deep enough to drown entire cities. The pumping was real, and nowhere near enough. That is broken supersymmetry against the monster. So the most elegant idea in physics, the great hope of a generation, cannot save us. Even at its best, it leaves an error that would still shame any other theory in existence. And that leaves physicists facing something they hate even more than a wrong answer. A number that seems to be fine-tuned by hand, to a precision so absurd it looks like a miracle. When the elegant fixes fail, physicists are left staring at something that looks less like physics and more like a magic trick. To get the tiny vacuum energy we actually observe, all those enormous contributions must cancel each other with a precision so extreme it borders on the miraculous. And nobody ordered the miracle. Here is the situation once every proposed cure has fallen short. The vacuum energy is a giant sum of many separate pieces. Some pieces are positive, pushing the total up. Some are negative, pulling it down. Each individual piece is enormous on the scale of the monster prediction. When you add them all together, in a healthy theory with no special reason for them to cancel, you would expect the total to also be enormous, roughly the size of the biggest pieces. Instead, the total comes out fantastically tiny. The huge positive pieces and the huge negative pieces almost perfectly annihilate, leaving behind only the faint whisper we measure. The cancellation is nearly but not quite complete. Now ask how precise that cancellation has to be. The individual pieces are around 120 orders of magnitude larger than the surviving total. For the leftover to be as small as it is, the big pieces must cancel to something like 120 decimal places. Get the very first digit wrong, and the leftover is off by a factor of 10. Get the 50th digit wrong, and the universe looks nothing like ours. Every digit has to line up positive against negative flawlessly. There is no known reason for this. In supersymmetry, the deep symmetry was supposed to force the cancellation for free. Without it, the pieces have no reason to cancel at all. They are set by completely different parts of physics, with no obvious connection between them, and yet they conspire digit after digit after digit to erase each other almost perfectly, and to leave exactly the tiny crumb that lets the universe exist. Physicists call this fine-tuning, and they distrust it deeply. In science, when a result depends on a fantastically precise coincidence with no reason behind it, that is usually a sign you are missing something. Real explanations do not usually hinge on 100 lucky digits all falling into place by accident. Imagine you are told that 100 archers, standing far apart, each fired a single arrow, blindfolded into the sky at random, and every single arrow landed in the exact same tiny spot on the ground, stacked one on top of another. You would not call that luck. You would be certain there was some hidden mechanism, some unseen force, guiding every arrow to that one point. Chance does not produce 100 perfect hits. The vacuum energy is that impossible cluster of arrows. 100 enormous contributions from unrelated corners of physics, all landing so precisely that they cancel to leave one tiny surviving value, tuned just right for a universe with galaxies and stars and life. Either there is a hidden mechanism we have not found, or the universe pulled off a coincidence that should be impossible. Physicists find both options unbearable. A hidden mechanism should have shown up by now, and every candidate has failed. A pure coincidence violates everything they believe about explanation. Cornered, some of them reach for a way out so radical that it changes the meaning of explanation itself. They stopped asking why the number is what it is, and started asking whether it had to be anything in particular at all. There is a way to make the vacuum energy problem disappear that is technically allowed and deeply unsatisfying. You simply choose the answer by hand. The mathematics lets you dial the vacuum energy to any value you want, including the tiny one we observe. Many physicists consider this the same as giving up. Recall the trick from earlier, the one Paul Dirac hated. Renormalization, the surgery that cuts infinities out of quantum calculations by folding them into measured quantities. That same trick applies here, and it offers a tempting escape. When you calculate the vacuum energy and get a monstrous or even infinite answer, renormalization says you are allowed to add a correction by hand, a counter term to cancel the unwanted piece. You subtract off the monster and set what remains equal to whatever the experiments say. Since experiments show a tiny vacuum energy, you just choose your correction so that the leftover comes out tiny. The disaster is absorbed into a number you pick to match reality. On paper, this works. The mathematics does not forbid it. You can treat the vacuum energy as simply another basic constant of nature, a number that the theory does not predict but that you measure and plug in, like the mass of an electron. The theory never told you the electron's mass either. You measured it and moved on. Why not do the same with the vacuum energy? Measure it, insert it, stop worrying. Here is why this leaves almost everyone cold. To make the leftover come out as tiny as it is, your hand-chosen correction has to be tuned with that same insane precision, matching the monster to around 120 decimal places. You're not explaining the tiny value. You're choosing a giant correction, dialed to 120 digits for the sole purpose of cancelling the monster down to the size you already know the answer should be. That is not a solution. That is writing the answer you want at the bottom of the page and then arranging the math above it to arrive there. The precision that looked miraculous before has not been explained. It has just been renamed and moved into a constant you set by hand. Many theorists say this openly. Choosing the vacuum energy by hand, tuned to match observation, amounts to ignoring the problem rather than solving it. The whole point of the crisis was to explain why the number is so strangely small. Declaring the number to be an input you measure and refusing to ask why it has that value sidesteps the question instead of answering it. Imagine a student handed a fiendishly hard math problem. Instead of solving it, they look up the answer in the back of the book, write it down, and fill in fake steps that happen to lead there. They will get full marks. They have also learned nothing, and if you change the problem even slightly, they are lost. Setting the vacuum energy by hand is copying the answer from the back of the book. It matches, and it teaches you nothing about why. So the honest physicists were stuck. The elegant fix failed. The hand-tuned fix explains nothing. The coincidence looks impossible. Every ordinary road was blocked, and when every ordinary road is blocked, some minds turn to an extraordinary one. What if the reason the vacuum energy is perfect for life is simply that we could only ever exist in a universe where it was? There is an answer to the vacuum energy problem that flips the whole question on its head. It says the number is tuned for life because we could never have shown up in a universe where it was tuned differently. It is called the anthropic principle, and it makes many physicists deeply uneasy. The reasoning goes like this. Suppose the vacuum energy could take almost any value. In most cases, it would be enormous, and the universe would tear itself apart or crush itself instantly, with no chance for galaxies, stars, or life. Only in the rarest cases, where the vacuum energy happened to land in a razor-thin sliver near zero, would a universe stay stable long enough to build structure and eventually living things. Now here is the twist. If life can only arise in those rare, finely balanced universes, then any living being who measures the vacuum energy is guaranteed to find a tiny value. Tiny is the only kind of universe where observers can exist to measure, however unlikely tiny may be. A universe with a huge vacuum energy has no astronomers in it to be puzzled by the huge vacuum energy, so the smallness of the number in this view is a selection effect. We are seeing the only kind of universe that could ever contain someone to see it. The vacuum energy looks perfectly tuned for life because we are the ones looking, and we could only ever have appeared in a place where it was. This idea has a startling piece of history behind it. Years before the universe was measured to be accelerating, the physicist Steven Weinberg used exactly this kind of reasoning to make a prediction. He argued that if the vacuum energy was selected this way, it should not be exactly zero. It should be small, but just large enough to start affecting the universe around the time galaxies had finished forming. He put rough limits on how big it could be while still allowing observers like us. Then 1998 arrived, and the measured vacuum energy landed remarkably close to the range Weinberg had sketched out from anthropic reasoning alone. A prediction made by asking only what value would permit life turned out to roughly match what the cosmos actually revealed. That was a stunning, unsettling success. Think of walking into a vast library where every book is a different universe, each with its own vacuum energy printed on the cover. The overwhelming majority of books describe dead, structureless universes, torn apart in an instant. Only a vanishingly rare few describe universes calm enough for stars and life. Now notice something. You can only ever be reading a book from that rare shelf, because those are the only universes that produce readers at all. The tiny vacuum energy on the cover is not a surprise. It is the price of there being anyone to open the book. It is a clever, powerful, and slippery argument, and for it to make real sense, it needs one enormous thing to be true. It needs there to actually be a vast library of universes, a huge collection of real cosmoses with every possible vacuum energy, so that ours can be one of the rare habitable volumes. Without that library, the anthropic answer is just a story. So the question becomes unavoidable. Is there really more than one universe? And astonishingly, our best theories of fundamental physics seem to answer yes, in numbers beyond comprehension. For the anthropic answer to work, our universe has to be one of a staggering multitude, each with its own value of vacuum energy. And our deepest attempt at a theory of everything seems to deliver exactly that. It predicts a landscape of possible universes so vast, it makes the number 1 with 120 zeros look small. The theory in question is string theory, the leading attempt to unite all the forces of nature, including gravity, into a single framework. In string theory, the fundamental objects are not tiny points, but tiny vibrating strings, and the different ways they vibrate give rise to all the different particles and forces. It is mathematically rich and deeply ambitious. When physicists studied string theory closely, they discovered something they did not expect and were not sure they wanted. The theory does not pin down a single, unique universe. Instead, it allows for a colossal number of possible universes, each with different physical laws, different particles, and crucially, different values of the vacuum energy. The extra dimensions the theory requires can be folded up in an almost unimaginable number of distinct ways, and each folding produces a different universe with different properties. How many? Estimates run to a number with hundreds of zeros, often quoted as something like a 1 followed by 500 zeros, and possibly far more. Each of these represents a different possible universe, a different set of laws, a different vacuum energy. Physicists call this immense collection of possibilities the landscape. By itself, a theory that allows countless possible universes might just mean the theory is incomplete, unable to say which one is real. But pair it with certain ideas about the birth of the cosmos, and something wilder emerges. Some versions of how the universe began suggest that these possibilities actually get realized. Universe after universe springs into being, each settling into a different corner of the landscape, each with its own vacuum energy. The result is a multiverse, a vast ensemble of real, separate universes, each running its own version of physics. In that picture, the anthropic answer finally has the library it needs. Out of the enormous multitude of universes, the overwhelming majority have large vacuum energies and are dead, torn apart or crushed at birth. A rare few, by pure chance, land in the narrow habitable sliver near zero. And of course, the only universes that contain observers wondering about vacuum energy are the rare habitable ones. We find our vacuum energy tiny because we could only have arisen in a universe where it was. Picture an unimaginably vast beach, its sand made not of grains but of entire universes, more of them than there are atoms in everything we can see. Nearly all of these universe grains are lifeless, destroyed in an instant by their own vacuum energy. Scattered impossibly rarely among them are the few that stayed calm enough to grow stars and mines. We are standing on one of those rare grains, not because it was special or chosen, but because it is one of the only grains where standing is possible at all. It is a breathtaking idea. It might even be true. But a great many physicists look at it with something close to horror, because in explaining the vacuum energy this way, we may have paid a price that science can never get back. We may have given up the very thing that makes physics physics. The multiverse can explain the vacuum energy, and that is exactly why so many physicists distrust it. To many of them, it does not feel like a discovery, it feels like surrender. Because an idea that explains anything by saying every possibility exists somewhere may explain nothing at all. Here is the heart of the objection. The whole power of physics comes from making sharp predictions and testing them. A good theory says the world must be this specific way, and no other, and then you go check. When the theory is right, reality matches its narrow prediction, and you have learned something real about how nature works. That tight link between prediction and test is what separates physics from storytelling. The multiverse threatens to snap that link. If there are countless universes with every possible value of vacuum energy, then no value needs explaining anymore. Whatever we measure, the multiverse shrugs and says some universe had to have that value, and it happens to be ours. There is nothing to predict, because everything happens somewhere. For many physicists, that is a hollow answer. It can absorb any measurement without strain, which sounds convenient until you realize the cost. A theory that can accommodate any result forbids nothing, and a theory that forbids nothing cannot really be tested. You can never catch it being wrong, because it always has an escape. Critics say this makes the multiverse less an explanation and more a way of declaring the question unanswerable and calling that an answer. There is also the brutal problem of proof. The other universes, if they exist, are beyond our reach, separate cosmoses cut off from us, with no light and no signal ever passing between them and us. We can never see one, never visit one, never detect one. We are asked to accept an ocean of invisible universes on the strength of theory alone, to explain a single number in our own. To skeptics, that is a staggering thing to ask, so physics finds itself split. Some researchers accept the multiverse as the honest answer, arguing that nature is under no obligation to be tidy or to satisfy our craving for unique explanations. If the vacuum energy really is a lottery result, then demanding a deeper reason is a mistake, and the anthropic story is simply the truth, however uncomfortable. Others refuse, insisting that reaching for infinite unseen universes to explain one number is the moment science stops doing its job and starts telling comforting stories. Imagine a detective investigating a strange event. One detective keeps searching for the specific cause, the mechanism, the reason it happened this particular way. Another detective throws up their hands and says the event happened because, across enough possible worlds, everything happens somewhere, so there is nothing more to explain. The first detective might be chasing a cause that does not exist. The second might be abandoning a real explanation out of despair. Nobody can yet say which one is right. This is where the vacuum energy crisis has driven some of the finest minds in physics to a fork between accepting a boundless multiverse and rejecting the whole approach as a dead end. But the multiverse is only one of several paths physicists are exploring. Because as unsettling as it is, there is a deeper worry lurking underneath the entire problem. What if the mistake is hidden in the way we are asking the question, rather than in the number itself? There is a second strange coincidence buried inside the vacuum energy problem, and it may be even harder to explain than the first. Out of all the moments in the vast history of the universe, dark energy took over the cosmos right around the time we showed up to notice it. Physicists call this the cosmic coincidence, and it refuses to sit still. To feel the strangeness, you have to understand how matter and dark energy behave differently as the universe grows. Ordinary matter thins out as space expands. Spread the same amount of matter through a bigger and bigger volume, and its density drops. In the early universe, when everything was packed close, matter dominated everything, its gravity ruling the cosmos and slowing the expansion. Dark energy does the opposite. As the universe expands, dark energy does not thin out at all. It is the energy of empty space itself, so more space simply means more dark energy, holding steady at the same density everywhere, forever. It does not dilute. That difference sets up a cosmic race across the ages. In the distant past, matter was dense and dominant, and dark energy was a negligible afterthought. But as space kept expanding, matter kept thinning while dark energy held firm. Eventually, inevitably, dark energy had to overtake matter, seizing control of the universe and switching the expansion from slowing to accelerating. Here is the coincidence. That crossover, the moment dark energy finally overtook matter, happened in the relatively recent past, cosmically speaking, and it fell in the same era in which stars, planets, and living observers came into being. Out of the entire 14 billion year history of the universe and the far vaster future ahead, the handover from matter to dark energy lines up roughly with the arrival of creatures able to measure it. Why should those two things coincide? There is no obvious reason the balance point between matter and dark energy should fall anywhere near the era of observers. It could have happened long before any galaxies formed, in a universe that then expanded into cold emptiness. It could happen trillions of years in the future, long after every star has died. Instead, it falls, suspiciously, right around cosmic now. Picture two runners on a track, one gradually slowing and one holding a steady pace. At some single instant they draw exactly even, before the steady runner pulls ahead for good. Now imagine that the only spectators ever to watch the race happened to arrive in the stands at almost the exact moment the two runners were neck and neck. You would wonder whether the timing was rigged, or whether the spectators could only exist at that particular moment for some reason you had not grasped. The cosmic coincidence is that suspicious timing, written across billions of years. Some physicists think it is a clue, a sign that dark energy and the emergence of structure are linked by something we do not yet understand. Others fold it into the anthropic story, arguing that observers can only arise in a window near the crossover, and a few suspect it is telling us that our whole idea of dark energy as a simple constant is wrong. That last suspicion has been growing, because a small but determined group of physicists has never accepted that we are stuck with a fine-tuned number or an ocean of universes. They think the mistake is hiding somewhere in our assumptions, and they have gone looking for it in the strangest places, including in the nature of gravity itself. A bold group of physicists asked a question that turns the whole problem inside out. What if the vacuum energy really is enormous, exactly as the theory predicts, but gravity simply refuses to feel most of it? The mistake in this view lies in our assumption that gravity responds to all of it, rather than in the size of the vacuum energy. Recall the deep link at the center of this crisis. Quantum theory calculates a huge vacuum energy. General relativity says any energy in empty space bends the cosmos and drives its expansion. The catastrophe comes from bolting those two statements together. The vacuum energy is huge and gravity feels all of it, so the universe should be destroyed. But look closely at that chain. There are two assumptions there, not one. The first is that the vacuum energy is huge. The second is that gravity responds to every scrap of it. Almost every attempt to fix the problem has attacked the first assumption, trying to make the vacuum energy small. This group attacks the second. What if the vacuum energy is huge, and gravity is somehow blind to nearly all of it? This idea goes by names like degravitation and modified gravity. The proposal is that gravity might act like a filter, for energy that is smooth and unchanging everywhere, spread perfectly evenly through all of space with no variation. Gravity might barely respond at all, and the vacuum energy is exactly that kind of energy. It is the same at every point, featureless, uniform, filling the void identically everywhere. Perhaps gravity, for reasons rooted in some deeper theory, simply does not grip smooth, constant energy the way it grips lumpy matter. If that were true, the monstrous vacuum energy could be sitting there real and enormous, and yet exert almost no push on the cosmos, because gravity looks straight through it. The huge number would be genuine but harmless, filtered out by the way gravity actually works. The tiny leftover acceleration we see would come from something else, a small residue or a separate effect. Picture a massive speaker playing a sound so low and so constant that it fills a room evenly, the same pressure in every corner, never changing. Now imagine your ears could only detect changes in sound, differences from place to place or moment to moment, and were completely deaf to a steady, uniform background tone. The speaker could be blasting at full power, and you would hear nothing because your ears filter out the constant part. In this idea, gravity is those ears, and the vacuum energy is the steady, uniform tone it cannot hear. This is a radical suggestion, because it means tampering with gravity itself, with Einstein's theory that has passed every test thrown at it. Any modification has to be incredibly careful, changing how gravity treats smooth vacuum energy, while leaving all its successful predictions untouched, from falling apples to orbiting planets to bending starlight. That is a razor-thin needle to thread, and no version has yet fully succeeded. Still, the mere existence of this approach reveals something important. The crisis might not be about the number at all. It might be about a hidden false assumption, a step we took for granted that turns out to be wrong. And once you start hunting for false assumptions, an even more unsettling possibility appears. What if the very act of adding up the vacuum energy, the calculation that produces the monster, is itself the mistake? Some physicists have started to wonder whether the giant vacuum energy is a genuine feature of nature or an illusion created by the way we do the calculation. In this view, the monster is a mirage. It appears only because of a flaw in how we add up the froth, and a correct calculation would never produce it in the first place. Go back to how the monstrous number is born. You take every field in space, count up its endless quantum trembles, from long ripples down to the tiniest ones, and add all their energies together. The reason the total explodes is those tiny ripples at the small end. As you head towards smaller and smaller scales, the ripples carry more and more energy, and the sum runs away toward the monster. This group of physicists points a suspicious finger at that step. Adding up ripples all the way down to the smallest scales assumes that our current physics still works perfectly at those scales, and that the naive way we sum the energies is the right way. Both assumptions might be wrong. The runaway sum might be an artifact, a fake infinity produced by pushing our equations into territory where they no longer apply, or by adding things up in a way that double counts or misrepresents what is really there. Several proposals try to show this. Some argue that when you account for deep symmetries that constrain the vacuum, the enormous contributions were never supposed to be added up so crudely, and a proper treatment leaves a far smaller, saner result. Others suggest that where gravity and quantum theory merge, at the smallest scales, the very notion of piling up ripple energies breaks down and the monster simply never forms. In these pictures, there is no 120 order of magnitude catastrophe waiting in nature. There is only a 120 order of magnitude mistake in a particular way of calculating. Fix the calculation, and the disaster dissolves, leaving behind something modest and manageable, perhaps even the tiny value we observe. Imagine you are measuring the area of a room by adding up the size of every object in it, but you accidentally count the same reflections in the mirrors as if they were real objects, over and over. Your total balloons to something absurd, a room bigger than a city. The room did not change. Your method was flawed, counting phantoms as if they were furniture. Some physicists suspect the vacuum energy monster is exactly this, a sum inflated by phantom contributions that a smarter method would never include. If they are right, the worst prediction in the history of physics was never a prediction about nature at all. It was a warning sign about our own mathematics, a red flag that we were adding things up the wrong way. The crisis would be real, but its lesson would be about the limits of our tools, rather than a genuine catastrophe hiding in empty space. Nobody has yet produced a version of this that convinces the whole field. Each attempt fixes part of the picture and stumbles somewhere else. But together all these approaches, the modified gravity, the mirage calculations, the deep symmetries, share one thread. They all suspect there is a hidden mistake in how we frame the problem, and that suspicion has been quietly building toward a moment when nature itself might reveal whether the constant we have been arguing about is even constant at all. To crack the vacuum energy problem, physicists needed to stop arguing and start watching dark energy directly, across the whole history of the universe. So they built a machine to map the cosmos on a scale never attempted before, capturing millions of galaxies to trace exactly how dark energy has behaved over billions of years. What it found is quietly upending everything. The machine is called DESY, the Dark Energy Spectroscopic Instrument, mounted on a telescope on a mountaintop in Arizona. Its purpose is single-minded. It measures the light from enormous numbers of distant galaxies and quasars, gathering the stretched light of objects scattered across billions of years of cosmic time. From that light it can chart where those galaxies sit and how the universe has expanded throughout its history. The scale of it is staggering. In its first years of operation, DESY gathered the light of around 15 million galaxies and quasars, building the largest three-dimensional map of the universe ever made. Each galaxy is a data point, a marker showing how much the universe had expanded when that light set out. String millions of them together across cosmic history, and you get a detailed record of how the expansion has sped up and slowed down over the past 11 billion years. Why does this matter for the vacuum energy problem? Because it lets physicists test the deepest assumption of all. Everyone had been treating dark energy as a true constant, the same yesterday, today, and forever, exactly like Einstein's cosmological constant. That assumption is baked into the whole crisis. The vacuum energy is supposed to be a fixed number, unchanging through all of time. DESY could finally check whether that is actually true. The idea is to watch how strongly dark energy has been pushing on the cosmos at different points in history. If dark energy is truly a constant, its push should have been the same strength throughout all of time, holding steady at every epoch DESY can see. But if dark energy is something subtler, its strength might have changed over the eons, stronger in the past and weaker now, or the reverse. The giant map can tell the difference. Think of it like studying old photographs of a river to learn whether its current has always flowed at the same speed. One photo tells you almost nothing, but thousands of photographs spanning centuries, each showing the river at a different moment, let you trace whether the current held steady or gradually shifted over time. Desi's millions of galaxies are those photographs, each capturing the cosmic current of dark energy at a different moment in the universe's past. For decades, physicists had no way to take these photographs in enough detail. Dark energy was a fixed assumption because we had no data fine enough to challenge it. The whole vacuum energy debate rested on the belief that we were dealing with a genuine constant, a single number to explain. Desi was built to finally put that belief to the test, to ask the universe directly whether its dark energy is the changeless thing everyone assumed. In 2024 and again 2025, Desi began delivering its answers, combining its vast map with other measurements of the early universe and distant exploding stars, and the results sent a jolt through physics, because the data started hinting at something almost nobody had dared to expect. The great constant at the centre of the worst prediction in science might not be constant at all. In 2025, the largest map of the universe ever made delivered a result that could rewrite the entire vacuum energy crisis. The evidence hinted that dark energy has been changing over cosmic time, weakening as the universe ages. If that holds up, the fixed constant everyone has been trying to explain for decades may never have been fixed at all. Desi released a major analysis drawing on its enormous galaxy map, combined with measurements of the ancient light left over from the young universe and observations of distant exploding stars. Together, these let physicists reconstruct how strongly dark energy has pushed on the cosmos at many different points across the past 11 billion years. If dark energy were a true constant, its strength would have been identical at every epoch. That is what almost everyone expected to find. That is not what the data showed. When physicists pieced together the full picture, they found signs that dark energy has not held steady. Its push appears to have been stronger in the distant past and to have weakened as the universe grew older. Taken on its own, Desi's map still fits a simple constant well enough, but combined with the other measurements, the results lean toward a dark energy that evolves, drifting away from the fixed value the cosmological constant demands. The scientists were careful, and rightly so. This is a hint, not a verdict. When they combined all their data, the evidence reached a level of confidence that is exciting but short of the gold standard physicists require before declaring a discovery. Physics has been fooled before by signals that faded once more data arrived. So the Desi team spoke carefully, saying the standard picture may need updating, and that a changing dark energy now looks like a real possibility. But sit with what it would mean if the hint holds. For the entire history of this crisis, the vacuum energy was assumed to be a single fixed number, and the whole nightmare was explaining why that number is so absurdly small. If dark energy is instead something that changes over time, then it may not be the raw energy of the vacuum at all. It might be a new ingredient in the universe, a field that evolves, with its own behaviour and its own rules, related to the vacuum energy but not identical to it. That would crack the problem open in a completely new way. A changing dark energy would mean the thing driving the cosmos apart is dynamic and alive, not a dead constant. And it would suggest that the monstrous vacuum energy from quantum theory and the gentle push accelerating the universe might be two different things after all, connected by physics we have not yet discovered. Picture generations of scholars arguing furiously about the exact fixed height of a distant mountain, building elaborate theories to explain why it stands at precisely that height. Then someone brings a far better telescope, looks carefully, and realizes the mountain is not standing still at all. It is slowly rising and falling, breathing, changing height over time. Every theory that assumed a fixed height was aimed at the wrong question from the start. The Desi hints raise the possibility that dark energy is that breathing mountain, and that we have been trying to explain a constant that was never constant. If that is true, the mistake physicists could not ignore may finally be pointing somewhere, straight toward new physics and toward a reckoning with the fate of the universe itself. If dark energy really is changing, then the greatest embarrassment in physics transforms into something else entirely. The mistake stops being a wall and becomes a doorway, because a wrong prediction that finally starts leaking clues is no longer just a failure. It is a trail leading toward physics we have never seen. For decades, the vacuum energy problem felt like a dead end. The theory gave a monstrous number. Reality gave a whisper. Every attempt to bridge the gap either failed or explained nothing. The mistake just sat there, enormous and mute, refusing to tell anyone where the error lived. It was the worst prediction in science, and it seemed to lead nowhere. A changing dark energy changes that completely. If Deasy's hints hold, then dark energy is not a fixed cosmological constant, but something dynamic, a field spread through space that evolves over cosmic time. Physicists already have candidates for what such a thing could be. They imagine a new kind of field filling the universe, slowly shifting its value over billions of years, its strength gently fading or growing as the cosmos ages. This evolving field would be a genuinely new piece of physics, a new ingredient in nature beyond anything in our current theories, and crucially, a dynamic dark energy might sidestep the monster entirely. The catastrophic prediction came from treating dark energy as the raw, fixed energy of the vacuum. But if the acceleration is driven by a separate evolving field, then the true vacuum energy might genuinely cancel to zero through some deep principle we have yet to find. While this new field provides the gentle push we actually observe, the impossible fine-tuning problem could split apart, one piece solved by a clean cancellation to zero, the other handled by a new field with its own natural behaviour. That would be a stunning turn. It would mean the century-long struggle to explain one absurd number was partly a case of mistaken identity. We were trying to explain why the vacuum energy is tiny, when the thing accelerating the universe may not be the vacuum energy at all, but a new and dynamic actor wearing its disguise. The mistake would have been hiding a discovery inside it the whole time. None of this is settled. The evidence is still a hint, still short of proof, still waiting on more data from DESI and the observatories racing alongside it. It is entirely possible that as the measurements sharpen, the signs of change will melt away, and dark energy will settle back into a boring exact constant, leaving the old nightmare fully intact. Physics has seen tantalizing signals evaporate before, but the possibility alone has electrified the field. For the first time in a long time, the vacuum energy problem has become a source of expectation rather than only embarrassment. The universe itself, through the largest map we have ever made of it, may be handing us a new clue about the deepest mystery in physics. And if the clue is real, it will not stay confined to a debate about one number. Because the strength and behaviour of dark energy does something no other quantity in physics does. It decides how the entire universe ends. Whether space expands gently forever, or tears itself apart, or reverses and collapses, all of it hinges on the nature of this push. The mistake physicists cannot ignore is bound up with the ultimate fate of everything that exists. The vacuum energy is not only the worst prediction in the history of physics, it is the hand on the throttle of the entire universe. The exact nature of this one quantity determines whether the cosmos drifts quietly into darkness, rips itself to shreds, or reverses course and crushes itself back to nothing. Every possible ending hinges on it. Everything we have uncovered points to this. Dark energy, the energy of empty space, is what drives the universe to expand faster and faster. And how that expansion plays out over the far future depends entirely on how dark energy behaves, on whether it holds steady, grows, or fades over the endless ages to come. Consider the possibilities. If dark energy is a true fixed constant, holding its strength forever, then the universe will keep accelerating gently for all time. Galaxies will drift ever farther apart until each one is alone in an ocean of empty black, cut off from all the others as the space between them stretches beyond the reach of light. The stars will slowly burn out one by one until the cosmos fades into a cold, dark, endless quiet. A long, gradual death by isolation and cooling. But suppose dark energy is dynamic, and suppose it grows stronger over time. Then the acceleration could intensify without limit, and the push driving space apart could become so violent that it overwhelms everything. First galaxies are torn from each other, then stars ripped from galaxies, then planets from stars, then atoms themselves pulled apart until the very fabric of space shreds every structure in existence. A universe that ends not with a whimper, but by tearing itself completely to pieces. Or suppose the opposite. Suppose dark energy fades and weakens, exactly the direction the recent hints seem to point. Then in the far future its push could die away, letting the gravity of all the matter in the cosmos reassert itself. The expansion could slow, halt, and reverse, sending the entire universe falling back together, collapsing toward a final crushing point, undoing the expansion that began with the birth of everything. 3 possible fates: a slow cold fade, a violent tearing apart, or a final collapse. And which one awaits us is written into the nature of dark energy, into the exact behaviour of this single quantity that our best theory got so catastrophically wrong. Picture standing at a railway switch where 3 tracks diverge into the far distance. One track leads gently downhill into a cold and endless dark. One leads to a cliff where everything is torn apart. One curves back around toward a fiery collapse. The entire universe is the train, already moving, already committed to one of these tracks, and the switch that decides which track it takes is the nature of dark energy, the very thing hidden inside the worst prediction in science. This is why the mistake cannot be ignored. It reaches far beyond an academic puzzle on a page. It is tangled up with the destiny of all things, the final chapter of the cosmos, the answer to how the universe itself will end. And we do not yet know which ending is written, because we do not yet understand the quantity that decides it. Which leaves us standing at the edge of the deepest question of all. What is this mistake really telling us about the limits of everything we think we know? We have followed the worst prediction in the history of science all the way to its final meaning, and that meaning is humbling. The vacuum energy problem is a message from the edge of human understanding, a sign that something enormous is still missing from our picture of reality. Gather up everything we have seen. Empty space is boiling with energy, proven by atoms that get kicked and metal plates pushed together by nothing. Quantum theory can calculate that energy, and it hands back a number too large to believe, off from reality by around 120 orders of magnitude, a mistake bigger than every atom in the visible universe. The most beautiful fix, supersymmetry, was hunted for in the greatest machine ever built and never found. Setting the number by hand explains nothing. An ocean of universes explains it only by surrendering the spirit of science. And now the largest map of the cosmos ever made whispers that the number may not be fixed at all. Every road leads to the same conclusion. Our 2 greatest theories, quantum physics and gravity, the twin pillars holding up all of modern science, do not fit together. Each one is magnificent on its own. Quantum theory rules the world of the tiny with unmatched precision. General relativity rules gravity and the cosmos with equal glory. But force them to talk to each other about the energy of empty space, and they produce an answer so absurd that the universe itself proves it wrong just by existing. The 2 pillars do not meet. There is a crack running between them, and the vacuum energy problem is where that crack breaks the surface. That crack is the real discovery hiding inside the worst prediction ever made. It is telling us, in the loudest possible voice, that we do not yet have the deeper theory that unites the small and the large, the quantum and the gravitational. Somewhere beyond both of them lies a truth we have not grasped, a way of understanding reality in which the energy of empty space finally makes sense. The mistake is the shadow cast by that missing truth. Imagine explorers who reach the shore of an ocean no map has ever shown. They cannot cross it yet. They do not know what lies beyond it. But the mere fact that the ocean is there, vast and unexpected, tells them the world is far larger than they believed, and that a whole continent of discovery waits on the other side. The vacuum energy problem is that unexpected ocean. It marks the boundary of the known, and it promises that something greater lies past it. This is why physicists cannot ignore the mistake, and why they keep returning to it decade after decade. It is the sharpest sign we have that our understanding of the universe is incomplete. It sits at the exact spot where our best theories break, pointing straight at the next revolution in physics, the one that has not happened yet. The room around you is still boiling with that quiet energy. It has been there the whole time, in every empty space you have ever stood in, holding a secret our finest minds have chased for 100 years. The answer, when it comes, will change what we know about existence itself. And somewhere out there, in the froth of the vacuum, the universe is still waiting for us to understand what it has been trying to tell us all along.